Hi, this is the second part of the video for Chapter 8 on nonlinear regression functions. And in the last video, we looked mostly at polynomial models and as one way of modeling nonlinearities. Now we're going to turn to logarithms and see how we can use logs to model nonlinearities in regression functions. And so there's two, situations when logs are very useful. One is whenever you want to model elasticities. And we'll see an example of this later, but like the percentage change in the quantity demanded over the percentage change in price is the elasticity of demand. We'll see an easy way to estimate these elasticities when we use log models. And another reason logs are useful is when there's multiplicative relationships. For instance, I don't know if you've seen this or not, but if you keep taking economics, you will. There's something called a Cobb-Douglas production function that says y output is equal to some constant a, let me call it a prime, times labor to the alpha and capital to the beta. Often alpha plus beta, it gives you whether you have increasing or decreasing returns to scale. If alpha plus beta equals 1, you have constant returns. And so you might be interested in testing whether there's constant returns to scale, whether alpha plus beta is 1. What you can do, this is a nonlinear model. We can't estimate this with the stuff we've used. But if I take the log of y, that's the log of a prime plus alpha log L plus beta log K. And we can throw in an error. There's a way to get an error in the original function. I didn't quite do that. So you could just call this variable, say y tilde is the log of y, is beta 0, which is the log of a prime, plus beta 1 times the log of L. So that's your x1 plus beta 2 log of capital. That's your x2 plus the error term. And then you could test whether beta 1 plus beta 2 equals 1 or is less than 1 or greater than 1. But notice that we've taken a highly nonlinear multiplicative model and turned it into a linear model that we can estimate easily. So y tilde is just beta naught plus beta 1 x1 plus beta 2 x2 plus u. That's our standard model. x1 is the log of L. So in your spreadsheet in Excel, you'd have a whole bunch of L's. Maybe this is across a bunch of different firms. So you have the labor in each firm. Then the next column would just be the log of L. Then you've got the capital amounts in each firm. The next column would be the capital, log of the capital. And then you'd have another that was the log of output. Then you just regress the log of output on the log of labor and the log of capital, and you'd have a model. And then you can test things about these coefficients. And the third way in which logs are useful is for growth models. So there's a third application, which is growth models. When you do growth, it's like y is, say, beta naught e to the beta 1 x. This is basically the growth rate. And so this will grow at an exponential rate over time. If I make this negative, then you get a decay over time. It's called a decay rate. And so if beta 1's negative, you get a decay rate. And if beta 1's positive, you get growth, like population growth or something like that. And so growth models are almost always of this form. And if you want to estimate this, what you can do is say, well, the log of y is log of beta 0 plus beta 1x, because the log of e is just 1. The log and e are inverse functions. If I just call this, again, y tilde is beta naught tilde plus beta 1x, I can estimate this with standard sorts of techniques. I just let beta 0 tilde be the log of beta 0, and beta 1 is beta 1, y tilde is the log of y, and I can estimate this with our standard OLS model. And so logs have quite a few uses for modeling nonlinearities. And just a few things about logs, and then we'll move on to write down some models. So when you say y equals e to the x, that's a growth model. It's just a simple form. I just want to make sure, and remember e is just a constant. It's 2.7, can't remember this one, 828, it goes on and on. So e is just some number. Sometimes you write this as y equals exp of x. There's different ways to write it, but it's a growth function. And the general growth function would have a beta 0 here and a beta 1 there. Don't worry about that for the moment. What I just wanted to note is that the log of e to the x is x. And so log and e are inverse functions. So the log is the inverse of e, and e is the inverse of the log. And so those are inverse functions. If you look at that, if you put y here and x here, y equals log x looks something like this. The slope of that function is 1 over x. So as x goes to infinity, the slope goes to 0 eventually. And then it goes down here. It asymptotes to negative infinity down here. So log of 0 is minus infinity. This is 1. Log of 1 is 0. Just for some facts. So let me just write a few more things down about logs, just in case you've forgotten. The log of 1 over x is minus the log of x. That's often useful. The log of ax is log a plus log x. The log of x over a is log x minus log a. And the log of x to the a power is a log x. And so those are useful things. Now logs are also related to percentages. So let me see if I can make that connection clear. Because if I want the percentage change in x over time, I could take the log of x at time t minus the log of x of t minus 1. Like this might be GDP. If I take the log of GDP today minus the log of GDP last year, this year, last year, t minus 1, that would be the percentage change in GDP. That'd be GDP growth. So you can get growth rates out of the difference in logs like that. Now, how does that come about? We'll start with y equals the log of x. If you remember your calculus, dy is dx over x. dy dx is 1 over x. If I write that in discrete terms, use the triangle that doesn't scare you so much, it's this. The change in y is the change in x over x. But the change in x over x is just the percentage change in x. And so this quantity, dx over x, is the percentage change in x. So what that tells me is, let's start with, so what is d log y? Well, d log y is dy over y, which is the percentage change in y. And so when you take the d log y, what this is a discrete form. This means percentage change. Delta log y is dy over y. Again, it's the percentage change in y. And that's what this here, this is d delta log x. This is something like log yt minus the log of yt minus 1. That'd be the change in the log of y over time. And that's equal to the percentage change in y. And so logs are closely related to percentage changes. And this is the formula. Whenever I want to do percentage changes when I'm doing econometrics, and I want the percentage change in, say, GDP, you just take the log of GDP today minus the log of GDP last year, and you get the percentage change. And so it's a fairly easy way to get a percentage change. So again, so what we're saying is delta log y is approximately equal to the percentage change in y. And the smaller the change, the closer the approximation. And we'll have some other approximations for logs in a minute. Okay, so there's 3 logarithmic models that we're going to worry about. One's called log linear, another's called linear log, and the third is called log log. And it depends upon whether y or x are logged. So let me show you. So the 3 models are the following. So the 3 log models. Excuse me. The first is linear log. Y equals beta 0 plus beta 1 log xi plus ui. And you could extend this to more than 1x. I'm just using 1x to make it simple. So this would be called linear log. Linear here, log there. You could also have the log, I should put it yi there. The log of yi is beta 0 plus beta 1 xi plus ui. This would be log linear. That would be a log linear model. And the last case is log log. Log yi is beta 0 plus beta 1 log xi plus ui. So let's look at each of these 3 models and talk a little bit about what their properties are. So we'll start with the linear log model. Okay. In this model, a 1% change in x, so a 1% change in x, gives you a change in y equal to 0.01 times beta 1. And I'll show you how to get this in a second. And so in this model, if you increase x by 1%, y will change by 0.01 times beta 1. And so it gives you that sort of a relationship between y and x. The way you get this result, let me derive it. The change in yi is equal to beta 0 plus beta 1 log of x plus delta x, estimated change, so we're not using the ui's, minus beta naught hat plus beta 1 hat log of x. Okay? So x might be 100, and we're going to increase it by 1, so this is 101, and this is 100, so we're looking at a change from, say, 100 to 101, something like that. The change in y would be equal to this. So that's equal to, the beta zeros cancel, beta 1 hat times the log of x plus delta x minus the log of x. But we just learned that when you have a difference, that you can rewrite that as beta 1 hat times the log of x plus delta x over x. Because the log of a over b is log a minus log b. And we're using that to do this. So that's equal to beta 1 hat times the log of 1 plus delta x over x. Now here's where I need a new approximation. You can show, I'm not going to do it, but you can show relatively easily that the log of 1 plus delta x over x, or delta y over y, or delta a over a, or anything like that, is approximately equal to delta x over x when the change in x is small. So this approximation holds so long as your change in x isn't very big, like 1 or something like that we've been looking at. So this is then equal to, this down here is equal to beta 1 hat times delta x over x, which is beta 1 hat times the percentage change in x. So the change in y in this model for a 1 unit change in x is just beta 1 hat times the percentage change in x. So that's where that result comes from that we wrote down earlier. So if this is 1%, which is 0.01, then the change in y is 0.01 times beta 1 hat. Like that's where that result came from that we wrote down earlier. So getting the change in y for a 1% change in x is just beta 1 hat in this model. And so this is useful when you're talking about percentages rather than levels. You can still, as I said earlier, estimate this model with OLS. There's no problem with doing that. Again, the original model is just yi equals beta naught plus beta 1 log xi plus ui. You just use that as your variable, regress y on a constant and the log of xi, and you can use the standard OLS stuff we've already learned. And so there's estimation, hypothesis tests, confidence intervals, all of that stuff are exactly the same as they were before. So there's nothing new there. Let's look at the test score example. If you were to estimate that model for the test score example, you would get score hat is equal to 557.8 plus 36.42 times the log of income for I. And this is 3.8 is the standard error there, hugely significant constant. 1.40, that's going to be greater. If I divide that by that, that's greater than 2, so that's hugely significant. And R bar squared here is 0.561. And so no problem. So if income goes up by 1%, then y goes up by 0.01 times this number by 0.3642. So that's how you interpret this kind of a model. You could also do it in the original units. In other words, if I want to say, I don't want to talk about percentages, but I want to talk about dollars, you could say, what if y goes up from 10,000 to 11,000? What would happen? Well, there what you do is just what you did before. You take 557.8 plus 36.42 times 11 minus 557.8 plus 36.42 times 10, and you would get 3.47 if you did that. If you do it for 40 to 4, like we did before, 40 to 41, 40,000 to 41,000. So this is 10 to 11. This is 40 to 41. So we would do 41 here minus 557.8 plus 36.42 times 40. Then you're going to get 0.90. So you can see that we have a nonlinear relationship. The effect of x on y depends upon the value of x. When x starts at 10, you get a much bigger effect than when x starts at 40. For the same, it's a different percentage change. The percentage changes are the same, but in absolute magnitude, this is a much smaller percentage change, and you get a much smaller change in y out of it. So there's an underlying nonlinear relationship there. In fact, if you were to plot this, what it would look like is a model like this. The data would be scattered around a model that looked like that, where this is x, this is income, and this is score, y. And there's a picture of that in your book. If you want to take a look at it, that's figure 8.5. So that's the linear log model. Okay, the second case is log linear. So that's the model where, so this is model 2, log linear. And that's where the log of yi is beta 0 plus beta 1 xi plus ui. No log there anymore. The log's over here now. In here, a 1 unit change in x, that is delta x equals 1, gives a 100 times b1% change in y. To look at that one, say the log of y plus delta y is beta 0 plus beta 1 times x plus delta x. So if I change x by delta x, y changes by that amount. In that case, then, the log of y plus delta y minus the log in y, that's the change, would be equal to beta naught plus beta 1 times x plus delta x minus beta naught plus beta 1 times x. So the log of y plus delta y over y, bringing that into there, the beta naughts cancel, beta 1 x's cancel, is beta 1 delta x. This is, again, this is the log of 1 plus delta y over y. That's approximately equal to the percentage change in y. So the percentage change in y is just beta 1 delta x. So what beta 1, if this is 1, what beta 1 gives you is the percentage change in y for a unit change in x. So beta 1 is the percentage change in y for a unit change in x. And if we estimate that model using the test score data, what you will get is, oh, excuse me, this is earnings on age. This is a different model. I don't know why they switched on us, but they did. So the log of earnings hat predicted is 2.811 plus 0.0096 times age. R bar squared is 0.034, not so good. 0.0004 is the standard error there. 0.018 is the standard error there. So if age goes up by 1, earnings goes up by 100 times this, 0.96%. And so you interpret that model this way. In the third case, probably the most common use of the log models is the log-log. So the third case is log-log. Log yi is beta 0 plus beta 1 log xi plus ui. So that would be our third example. What beta 1 in this case is the percentage change in y over the percentage change in x. It's an elasticity in general. For instance, for y equals quantity and x equals price, it'd be the percentage change in quantity over percentage change in price, which is a standard elasticity. If you want to derive this result, let me show you how to get that result. Just find the change in y. The log of y plus delta y minus the log of y is equal to, first this, beta 0 plus beta 1 log x plus delta x minus beta 0 plus beta 1 log x. Bring this inside, so the log of y plus delta y over y, bringing that inside, is the beta knots cancel as beta 1 times the log of x plus delta x over x. And this is so the log of 1 plus delta y over y is beta 1 times the log of 1 plus delta x over x. And for small changes, these are approximately equal to delta y. So approx equal to this. This is approximately equal to delta y over y is beta 1 delta x over x. But these are just percentage changes. So the percentage change in y is beta 1 times the percentage change in x. So beta 1 is nothing more than percentage change in y over percentage change in x. So that's how you interpret beta 1. So whenever you want to estimate elasticities, it's really nice to just estimate a log-log model because the beta 1 coefficient is the elasticity. If we use the log score hat, estimate that model as a log-log, you get 6.336 plus 0.0554 log of income. And the standard errors are 0.006, I hope I copied that right, and 0.0021. This is all in the book. So what this tells us is if income goes up by 1%, score goes up by 0.0554%. And so these connect percentage changes in a fairly simple way. And so those are the three log models. All are different ways of measuring of modeling nonlinearities. And again, that third way, the log-log model, is probably the most popular of the three. remember the first model was y equals beta 0 plus beta 1 log x plus u. And that essentially gave you something that looks like this in terms of the nonlinearities. What does this model give you? Beta 1 x plus u. Well, take e to the both sides. E to the log y is just y. So what this tells you is y is equal to e to the beta 0 plus beta 1 x plus u. Or it's e to the beta 0, e to the beta 1 x, e to the u is another way of writing it. That's basically a growth model. So in this case, you're getting something that looks like this. If beta 0 plus, if this is a positive coefficient, if it's negative, you're getting a decay over time. And so this gives you both decays and growth as your model. So if your data look like this, that's going to be a negative coefficient. If your data look like this, that's a positive coefficient. And the third case is really, remember we started with a Cobb-Douglas production function? That third case, the log-log models, when you have multiplicative relationships. So I have y equals beta 0 prime x1 to the beta 1, x2 to the beta 2, and so on. Then the log of y is the log of beta 0 prime plus beta 1 log x1 plus beta 2 log x2. I could throw in an error too as well, just make it multiplicative. So the log-log model is really when you have these kinds of multiplicative relationships is when that model's useful. And so those are the three ways in which you can use logs. Okay. The last way we want to look at doing, allowing for nonlinearities in the relationship are interactions. These are when we have terms like x1, x2, x3, x4, x1, x8, something like that. We multiply two of the x's together. Those are called interaction terms. There's three types of interactions. We can interact two binary variables. We can interact a binary with a continuous, and we can interact two continuous variables. So I'll go through all three cases, and that'll take us to the end of this chapter. All right, so let's start with interactions between two binary variables. Let me see if there's anything else I wanted to say here. These are useful when, suppose that the effect of class size on scores depends upon the percentage of English learners that are in the classroom. So when you change class size, you have a different effect on score depending upon how many English learners you have in your classroom. That's where interactions become useful, is when the effect of one variable depends upon the magnitude of another variable. And so we'll look at examples like that. So let's first look at interactions of binary variables. Those are dummy 0, 1 variables. So say we have a model that's yi is beta 0 plus beta 1 d1i plus beta 2 d2i plus ui. This is the log of earnings. So we're going to have a log linear model here, but that's not important. The logs are not important at all in this case. What we're going to look at is the interaction. This is d1i is equal to 1 if you have a college degree and 0 otherwise. And so it's a dummy variable indicating that you graduated from college or not. D2i, this one, is 1 if female. If you're a woman, 0 otherwise. So we're letting the log of earnings depend upon whether you have a degree or not and whether you're male or female. But, and we don't have any interactions yet, but suppose that the effect of a degree on earnings depends upon whether you're a male or a female. And so the effect of a degree is different depending upon whether you're male or female. Well, this model doesn't have that effect in it. So what if the effect of degree on earnings depends upon gender? How do we get that into the model? In this case, a degree doesn't matter. The effect of a degree is just beta 1, and it doesn't have anything to do with your gender. What we can do is add an interaction. So we say yi is beta 0 plus beta 1 d1i plus beta 2 d2i plus beta 3 times their product, d1i d2i plus ui. Now the effect of a degree will depend upon gender, and I'll show you that in a second. So let me rewrite the model up here at the top of the board so I have some space to write. So our model is yi is beta 0 plus beta 1 d1i plus beta 2 d2i plus beta 3 times the product d1i d2i plus ui. So that's the model. Can you see that? Yeah, good. I thought I might have written it above the camera range, but fortunately we didn't. So this is degree or not. Degree or not. And this is the male, female. It's 1. If you're a female, it's 1 here if you have a degree. So let's look at the change in y between having a degree and not having a degree. So the change in y will be, so what I want is the change in y to be the expected value of yi given d1i equals 1 and d2i equals some value minus the expected value of yi given d1i equals 0 and d2i is some value, 0 or 1. We're not going to specify what that one is. So d1i is having a degree, d2i is not having a degree. So this is the change in y between having a degree and not having a degree. So let's just plug these in. So this is beta 0 plus d1i is 1, so we got beta 1 times 1 plus beta 2 times whatever d2i is, 0 or 1, plus beta 3 times 1 times d2i, plugging in for those. This is 1 and this is d2i. So that's this term. That's your income if you have a degree, and it depends upon whether you're male or female, minus beta 0 plus beta 1 times 0, this is not having a degree, plus beta 2 times d2i, plus beta 3 times 0 times d2i. So those terms are going to go away when we do the subtraction. And the beta zeros are going to cancel when we do the subtraction. So what this difference turns out to be, that is then equal to beta 1 plus beta 3. So the change in y from no degree to degree is equal to beta 1 plus beta 3 d2i, where d2i is 0 or 1. So the effect of a degree in this model, because we have that interaction term, depends upon whether you're a male or a female. So if you're female, when d2i equals 1, the change in y is beta 1 plus beta 3. When d2i equals 0, if you're a male, the change in y is beta 1. So the model allows for a difference in the effect of a degree, the effect of d1i, based upon the value of the other variable. So you see that? And that wouldn't be true if we didn't have that interaction term. The beta 3 is on the interaction term. If it were the class size example, we could have an interaction. Well, we'll do that in a second. We're going to do that one. Okay, let's do next interactions between continuous and binary variables. So one variable will be continuous, one will be not continuous. It'll be a binary variable. So let's start with no interactions. yi is beta 0 plus beta 1 xi plus beta 2 di plus ui. This is again the log of earnings. This is years work experience. And this is college degree. In this model, the effect of an additional year of experience is the same for college grads and non-college graduates. But that might not be true. It may be that if you have one more year of experience, the effect on income, the increase in your income, is different depending upon whether you have a college degree or not. In that case, we want to add an interaction term. So let's allow for this. And to allow for it, what we need to do is change the model to have an interaction term. So to allow for it, we'll write the model as yi is beta 0 plus beta 1 xi plus beta 2 di plus beta 3 xi di plus ui. So that we have an interaction, a product term here. Now, the previous model basically just had two different intercepts because there was no slope coefficient, there was no xi. What this model does is allow for different slopes and different intercepts, depending upon whether di, you're a college grad or not. So for instance, when di equals 0, the expected value of yi is beta 0 plus beta 1 xi. When di equals 1, the expected value of yi is beta 0 plus beta 1 xi plus beta 2 plus beta 3 xi. So it's equal to beta 0 plus beta 2 plus beta 1 plus beta 3 times xi. So what you're doing when you throw in an interaction like this is you're allowing both the slope and the intercept to differ of your model depending upon whether you have a college degree or not. So one model could be like that, and the other could be like that, depending upon whether DI is 1 or DI is 0. And it could be any shape at all, as long as they're linear. But so we're allowing this interaction like this would allow for different intercepts and different slopes. Now you can, if you want to, just have different slopes. And the way you would do that would be to throw out that term, make beta 2 0, run that model. Then they have the same intercept and different slopes. You can also, if you leave this term out, what you'll have is different intercepts and not different slopes. So you can also have a model where you have just different intercepts with the same slope by leaving out the interaction term, beta 3 being 0. So you have the same slope but different intercepts. So it really just depends upon how you write the model. But the most general case when you add an interaction between a continuous and a dummy is that you're allowing for both a difference in slope and a difference in the intercept. You can test whether, you could use an F-test that beta 2 equals beta 3 equals 0 to see if the slopes and the intercepts are the same. Or you could do a t-test just to see if the intercepts were the same or the slopes were the same. Beta 2 equals 0 is a test for equal intercepts. Beta 3 equals 0 would be a test of equal slopes. And so you can test all of those sorts of things. So for instance, you may think that the MPC is different according to whether you're rich or not. That the poor maybe consume more of their incomes, have a higher marginal propensity to consume than the wealthy. Then you could allow for two different responses, two different slopes by adding these kinds of interaction terms to your model. So you can test things like that. And then the book, I'm not going to do the example, but the book applies this to the score data. And I'm going to let you go ahead and read that on your own. It's pretty simple and exactly what you would think. Finally, we can do an interaction between two continuous variables. So in that case, you might have something like yi is beta 0 plus beta 1 x1i plus beta 2 x2i plus beta 3 x2i x3i. That's the interaction plus ui. Where again, this could be log earnings for person I. This might be age. And this might be years of schooling. And if you look at the change in y due to a change in x1, that's going to be beta 1 plus beta 3 x2i, 1i. So the change in y due to a change in x1 depends upon the value of x2. How it varies depends upon the sign of beta 3. And so the effect of age on earnings, log earnings, depends upon years of schooling. And it's also the case that the change in y due to a change in x2 is beta 2 plus beta 3 x1. So the effect of schooling on earnings depends upon age. And so this allows the effect of one variable, one continuous variable, to depend upon the value of another. So whenever the effect of one variable in your model depends upon the value of another variable, then you're going to add these interaction terms to it. And again, the book does an application of this to the test score data. I'm going to go ahead and let you read that on your own. And so that ends chapter 8. One more to go. Chapter 9. See you soon.